Swayam Prabha. Digital India. Educated India.
So in this lecture, I wanted to talk about a certain classification of polymers. So in the last few classes, we were looking at chemistry of polymers, carbon, how it hybridizes, and what are the different ways in which it can make bonds with other elements. So now we go from there, and then we talk about various kinds of polymers. And the classification is not very unique. Okay, there is no very unique standard of classification. So the classification can be done by many means. So that's what I want to highlight today. So I mean, broadly speaking, you can define or classify polymers based on the origin. Are they obtained naturally or they are obtained synthetically, depending upon that. Okay. So we have on the left hand side, we have natural polymers. When we say natural polymers, these are polymers that are available in the nature, okay, without any human intervention. For example, wood, which contains cellulosic fibers, lignin and all that, and then natural fibers like wool and silk, and natural rubber from trees. Okay, so these are all polymers that are occurring naturally. Okay, so and then you can also think about biomacromolecules such as DNA, proteins, and various other biopolymers. Okay, so you can broadly classify polymers as natural polymers, or you can also think about synthetic polymers. So synthetic polymers are man-made; they don't exist naturally. Okay, but we make these synthetic polymers from other natural sources such as natural gas, petroleum, coal, and so on. Okay, so we take molecules from those natural sources, do some chemistry, do some catalysis, and try to build molecules into a polymeric form. And the number and variety of synthetic polymers are huge, because we know a lot of chemistry, different kinds of chemistry we can do, and then we can make different kind of polymers. So as I said, typically we start with the low molecular weight hydrocarbons like ethylene and benzene, which could be obtained from distillating crude petroleum, and then you make them react and form polymerization to a very high large molecular weight polymers, right? So even though we say these are two different classes, in many applications we also blend them. We will have several scenarios where how do we mix natural polymers with synthetic polymers. Okay, so here I have given some examples. So all of us use plywood, okay, for construction purposes, and this basically contains wood, which is basically cellulose, plus synthetic adhesives, and synthetic adhesives are actually some sort of synthetic polymers too. Okay, adhesives are also polymers. And then tires, the car tires, automobile tires, which includes a combination of both natural rubber from from plants as well as synthetic rubber mix, okay, in certain proportions. Okay, so one way of moving towards sustainability is to take the synthetic polymers and then mix with the natural polymer to the extent that it is possible, so that you don't fully depend on synthetic polymer, but try to have some sort of a balance. So there are some applications which you cannot get rid of synthetic polymers. So in those scenario, can you blend the synthetic polymers with the natural polymers so that you depend less on the synthetic polymers? Okay, so this is one general classification. This I say that it is based on the source or the origin of these polymers. Then we also classify polymers broadly depending upon how we process them. Okay, for example, we call set of plastics or polymers as a thermoplastic. Okay, so what we mean by thermoplastic is that you can actually take a material, you can heat it. When you heat it, it actually melts, it becomes a viscous liquid. You can pour it in a mold and then cool it, then the polymer will take the shape of the mold. Once you cool, become solidified, become a solid. Now if you can take that product, you can remelt it again. Okay, you can actually again apply heat, melt it back, put it in a different mold and make a different polymer too. Okay, so very simple example is PET bottles, right? PET bottles, you take a virgin PET resin and then you make an injection molding of a preform and then you blow mold and get a bottle. After you use the bottle, you collect it back, clean it, you can again heat it, make them into a resin, and then make something else. Maybe you can make a fiber out of it, or maybe you can make benches out of it, etc. Okay, and you can do this many times. Okay, an ideal thermoset polymer will not undergo any thermal or physical change due to this repeated heating. But in practical reasons, many times you will see small degradation. Polymer molecule may become smaller, slightly shorter. There could be a breakage of chains. There could be a small oxidation. So few minor physical chemical changes usually happens in a practical terms. Okay, but an ideal thermoplastic should be something that you can do this cooling, heating, molding repeatedly over many cycles. Okay, so there are several polymers. Actually, a large set of polymers that we employ are of this kind. Okay, so that's what we call as a thermoplastics. Okay, example, as I said, PET bottles, PET, polyethylene, polypropylene. These are all something that you can heat, convert into a liquid form or semi-liquid form, put it in a mold, cool it, and then you do this over and over in many different folds. Okay. Then there are other kind which is called thermoset. Okay, so thermosets are different in the sense, in the thermoset, if you heat it, they become harder, they become stiff. Okay, and if you apply more heat, it doesn't melt, it can actually only degrade. Okay, so these are called thermoset plastics, where by applying heat, you are basically making it harder and stiffer, and you cannot remake it again into another form. And the reason why this happens is because typically in the thermoset plastics, you add something called a curing agent or a cross-linking agent. Upon heating, they make many intermolecular contacts or bonds that makes them more stiffer. Okay, I already gave a couple of examples in the previous class. Vulcanization of rubber, phenolic resins. These are things which make more bonds by heating. So they become more solid, more stiff, more harder. Okay, and if you heat it again, you're not going to melt it, you're going to only degrade it. Okay, so there are certain applications which requires something like epoxy adhesives or of this kind. Okay, thermosets. So here we are basically classifying based on how we process them with heat. Okay, then there are other kinds. The thermoset example, if I have to say, as I said, vulcanized rubber, but also in household, we buy this something called araldite, right? You get two tubes, you have two liquids, you mix them together and you apply, and if you wait some time, it becomes solid. That's because these two liquids actually kind of cross link and form this very strong thermoset, okay, which you cannot melt it back. Okay, and as I said, rubber is another example. Now there are other kinds called elastomers. Okay, so elastomers are also thermoplastic, but they are a little bit more flexible like rubber. Okay, they are rubber like material, but at the same time you can actually process with heat. Okay, an example is this the soles that are used in shoes. Okay, is an example of an elastomer. Okay, so these are based on the processing method. We classify them as thermoplastic, thermoset and elastomers. So what we are saying, we are trying to think about classification of polymer. From the origin point of view, we classify them as natural and synthetic. That's one level. Or if you want to think about based on the processing method, then these are the three classes: thermoplastic, thermoset and elastomer. Right? Any questions at this point? Now, it is also possible to classify polymers based on a chemical family. Okay, so what do we mean by chemical family? Well, it depends on the key functional groups or the monomeric units that are there in the polymer. Okay, so based on that also you can classify. But before we do that, let us also remember that there are only few atoms or elements that are commonly found in polymers. Okay, for example, you would see in the backbone chain, okay, you will see carbon-carbon bonds, silicon, nitrogen, oxygen, sulfur and phosphorus, right? And then if you look at the pendant atoms basically means the side chain. Okay, so that can have either hydrogens or halogens like chlorine, bromine and fluorine. Can you think of any polymer that has fluorine in the side chain? Yeah, Teflon. Yes, Teflon. Any polymer that has chlorine in the backbone? PVC, right? Any polymer that has hydrogen in the backbone? polyethylenes, yeah, many of these olefins, right? Okay. So, now when we think about this backbone, this is very important because if you have only carbon-carbon bonds in the backbone, that becomes very difficult to degrade, because I already told you the carbon-carbon primary bond dissociation energy is very high. It's about 380 joules per kilojoules per mole. Okay. So, one way of thinking about making biodegradable polymer is to have certain bonds that are little easy to break, okay, which could be carbon and nitrogen in the backbone, or having carbon and oxygen in the backbone, or having carbon and sulfur in the backbone. Those bonds are little weaker. Many of the enzymes present in soil can actually break, hydrolyze those bonds. Okay. So, this is a very key aspect, that when you think about a biopolymer or a synthetic biopolymer, something degradable biopolymer, you have to somehow manage to have bonds that involve these other easy to break elements, okay, carbon, nitrogen, carbon, oxygen and stuff like that. And you know, these pendant drops atoms, you know, these we use different halogens and different things, mainly with regard to fire resistance, adding fire resistance properties, or to add strength and etc. Okay, we already noted that halogens have very high electronegativity. When you have polymers made with these halogen atoms, you would have a very strong dipole in the chain. So, you can have very strong cohesive density, cohesive energy density. So, you can make more tougher, stronger polymer. Okay. So, compared to, let us say, with the hydrogen. And then we also say something called commodity plastics. It depends on the cost and use. So, there are a class of polymers which are low cost and produced in large volumes. Example would be like polyethylenes and polypropylenes and PETs, etc. Okay, PVC, polystyrene, etc. And then there is another class which is called engineering plastics or performance plastics. Okay. So, these are specialty polymers which are quite costly, but they have superior properties, something very specific in terms of strength, in terms of its fire resistance and so on. So, okay. So, examples are something like this: nylon, polycarbonate used in printed circuit boards, and PEEK, etc. Okay. So, polyester ether ketone. And in these polymers, when we say superior properties, we mean that these polymers can have at least or minimum 15 megapascal of tensile strength, and you can actually use them beyond 100 degrees Celsius. Commodity plastics will not give you this much strength and will not operate under these conditions. Okay, so that's a difference. So, commodity plastic basically means of simple uses, like small packaging and small strength applications. Okay, whereas engineering plastics and performance plastics has to work with high strength conditions and high operating temperatures. Okay, so this is another way of thinking about classify them based on cost and use. So, now going back to this family, this, as I said, that we are about 100 years old with this polymers. So, a lot of polymers synthetically have been created. So, it's not possible to actually enumerate all of them, but people have actually classified them based on families. Okay, for example, under the heading of thermoplastic, we understand what thermoplastic is. What is thermoplastic? You can reheat it and reuse it. Yes, you can actually form them again and again by melting, cooling, molding and so on, right. So, under this condition, under this topic, okay, you have something called polyolefins. Okay. So, polyolefins are nothing but taking an alkene and then polymerizing it. Okay. So, under this heading you can see we have polyethylenes. Within polyethylenes you can have low density, high density, linear low density, ultra high molecular weight, cross linked. So, these are all commercially available different grades of polyethylene. Okay. Polyethylene can be synthesized like a linear molecule. You can also attach branches to it. Therefore, you can control whether you have a low density polyethylene or high density polyethylenes. Okay. By through chemistry manipulation, you can change how the chains grow, their molecular weights, the topology, and then therefore you create this kind of different density polyethylenes. And sometimes you also have this XPE, which is polyethylene is usually a uncross-linked polymer, but there is also a version which is a cross-linked polymer. Okay. So then you have polyolefin and ethylene copolymers. Copolymer means in a same chain you can have more than one monomers. Okay. For example, you can have ethylene vinyl acetate, it's called EVA. So it contains both ethylene group as well as vinyl groups together in this. Okay. Then there are ionomers in which ethylene and methacrylic acid are combined together as two monomers, okay, and built repeatedly. Then you can have polyolefins other than polyethylene. So polyethylene is a kind of almost a linear one, but if you think about polypropylene, polybutene, these are all branched polyolefins, okay, and it just, the list goes on. So then you have something called PVC, polyvinyl chlorides. Within polyvinyl chloride, you can have again certain varieties, certain categories. So you have polyvinyl chloride, and then chlorinated PVC is called CPVC, and then you have this, vinylidene, chlorine, vinyl chloride copolymers. Okay, you can also make a copolymer of PVC. Then there is another class called this polyvinyl acetate. Within that, you can actually have several subclasses. Then there is something called cellulose 6. This involves cellulose acetate, cellulose nitrate, and so on. So they actually are used for making membranes, cellulose membranes, and so on. Okay, and you can also have copolymers in terms of cellulose acetate butyrate and cellulose acetate propionate and ethyl cellulose. Okay, so cellulose is a backbone, and you keep changing certain side chains, add another copolymer, you can make variety of them. Okay, so the point is, if you think about polyethylene, it's just not one polymer. You have so many variety within, depending upon whether low density, high density, branched, linear. Then there is another level called crystalline amorphous. Okay, so the list is huge. I will not be going through all the things, but I will only kind of draw your attention to the number and variety of such polymers. Okay, so there are polymers which are made up of styrene. Okay, polystyrene is well known, but within that you have a high impact polystyrene. This high impact polystyrene is something used in your refrigerator inner compartments, right? That is actually made up of high density polystyrene. The low density or the foam polystyrene is one that we use for packaging. When you buy the fridge, it comes with the cushion, right? Expanded polystyrene. So polystyrene can be made in different ways. It can be made very hard. It can be made very soft, foamy kind also, depending upon how you polymerize them. So we have a bunch of styrene ones. This ABS is also very much used in automobile sector. This is nothing but acrylonitrile butadiene styrene polymer system containing 3 parts. Okay, they add these 3 parts to have better strength, the durability, and various other properties. Then we have a set of polyamides within which we have this nylon. Within nylon you have 6,6, 6,12, 6,11, several combinations, again related to how we make these monomers combine. Acrylics, polycarbonates, acetals, and polyurethanes. These are other set of classes of polymers. They are all thermoplastics. Okay, so you don't have to necessarily note down all these things, but just remember that there's a huge set of polymers, and we have classified them based on the functional groups. Okay, so here we call them styrenics because all of them will have a styrene as one of the monomer. Okay, so similarly, if you think about this aliphatic or aromatic polyamides, you will have amide group as one of the common building block. So polyesters, polysulfones, polyether ketones, it's just the list just goes on, right? And then you also have fluorocarbons, the pendant atoms, which is fluorine based rather than hydrogen based, which is very high strength, thermal resistant, heat resistant polymer, and Teflon is one example, but there are also many other Teflon like polymers for high strength applications. So then we have this thermosets. What are thermosets? What are thermosets? Yeah, so they become harder by heating, okay, because they cross link. Okay, most of the thermosets are cross link polymers. So here we have again epoxides, phenolics, unsaturated polyesters, and then you also have thermosetting polyurethanes. I also listed polyurethanes in the thermoplastic also, but there is also thermosetting version of a polyurethane, okay, depending upon whether you are able to cross-link it or not. Then we also have this rubbers, various kinds of rubbers, butadiene, isoprene, these are all well known. There is also styrene butadiene, SBR, and you can see that variety of combination is possible which has this rubbery properties. And then you have also inorganic polymers. So inorganic polymers includes silicons, phosphorescents, polysulfur nitrates. Okay, so it's not necessary that polymer should have only carbon based. It can be also inorganic material based. Okay, so all right. Now there are also other ways. So let's continue. So classification based on origin, based on processing conditions, based on chemical family, okay, and in that list we also classify polymers based on how they are made from a reaction point of view, okay. So typically polymers are made through 3 different chemical reactions. These are one, addition reactions, condensation reactions, and ring opening reactions, okay. So these are the broad set of reaction methodology through which we make polymers, and any polymer made through these ways we call them as addition polymer or condensation polymer or ring opening polymer, okay. So what do we mean by addition reaction? So addition reaction basically means that typically they will have carbon in the backbone and you basically add up in the in the main chain, okay, and if you count the number of atoms in the repeating units of the polymer and the monomer, they will be same number, equal number, okay. Very good example is ethylene. So ethylene monomer has 2 carbon, 4 hydrogens, okay, and then if you look at the repeating units of a polyethylene molecule or a polyethylene chain, in the same repeating unit you will have again C2H4 groups, okay. Only difference would have been a double bond would have been opened up and you have a single bond in the chain, the monomer would have a double bond, but as far as the atom numbers are concerned, you basically preserve the number of atoms in the monomer and in the repeating unit, okay. So it is basically through by opening the second double bond, you basically link the molecule together, okay, you basically add one by one, okay. So that's called addition polymer, right. And then I will probably give some examples later on. Then you have this something called condensation reaction or condensation polymer. So in this case the backbone contains not only carbon but it also will have other elements like nitrogen and oxygen. In this case when you link 2 monomers, typically a small molecule will be released, okay, because of this condensation reaction, and this small molecule can be like mostly water, but it could be also other molecules like ammonia and other stuff, okay. So therefore if you count the number of number of atoms in the repeating unit, that will be always smaller than the monomers you started off with because of this condensation that is happening. Some molecules are being released by this reaction. Then there is something called this ring opening reaction. In the ring opening reaction what happens is typically you will have a ring like structure and you break open the ring and make the molecule linear, and then you attach you attach the other monomers. Typically in these cases there won't be any release of monomers, okay, but the monomer will have some sort of a ring like structure. It can have a pentagonal ring, it can have a hexagonal ring, or it can have a trigonal ring, or it can have a square and all that, right. Okay, so now if we go a little further inside, we see that this there are 2 kinds of reactions which we call them as a step reaction and chain reaction. Most of the addition polymerization that I talked about, they occur through what is called a chain reaction, okay. And within this chain reaction there are 3 types. There are free radical, there are anionic, and there are cationic, okay. So if you just think about only how free radical reaction happens, okay. So free radical reaction goes through 4 stages. This free radical reaction is a type of a chain reaction, and chain reaction usually happens in the addition polymerization, okay. So here what you do is you have monomer, but they themselves will not react. So what you need is you need something called an initiator, okay. You need an initiator, and the initiator has this kind of a form. Okay, this is a peroxide in this case. I am showing how polyethylene is actually produced through a chain reaction, and chain reaction is an example of an addition reaction. Okay, and here within this chain reaction we are talking about free radical reaction. So free radical has to be created by adding something. What we do, we add an initiator, something like a peroxide. It is shown as ROR. So this R can be hydrogen, then you have hydrogen peroxide, or you can have R as some other groups also. Okay, you can have other methylene group or ethylene groups. So now when you heat, what happens is this initiator first will open up, you will create what is called a free radical. Okay, so this free radical, this entire step we call as an initiation. Okay, so in initiation you have an initiator, typically a peroxide, you apply heat and then it forms free radicals. Then this free radical is very reactive, highly reactive. The moment a free radical is created, it will go and attack a monomer. Okay, so let's say our monomer here is ethylene. So this is a CH2CH2, which is basically a methylene monomer. So what happens is that when your free radical attaches to this monomer, you see that this double bond is now opened up. Okay, and the free radical is moved to the carbon atom here. Okay, and here we have what is called dissociation step. One free radical attacking one monomer and then creating a free radical in the monomer itself. So then this will become, this can actually break many other monomers. Even though the first monomer is opened up by the free radical, but further subsequent free radical reaction can be initiated by the newly created monomer free radical. So you can see that this free radical is attacking another monomer, and then you have this kind of a chain growth. This is called propagation or chain growth, and this is also reason why we call as a chain reaction, because you start with the free radical from the initiator that creates one of this free radical. This free radical can go and attack other monomer and you create more free radical. This free radical can attack another monomer, so that's what we call a chain reaction. You basically make a very explosive number of free radical, and wherever the this monomer is available, they are going to just get added up to the main chain. Okay, but at some point of time you need to terminate it. Okay, because you don't want to grow a chain too long. Okay, you have certain range of molecular weight, you want certain number of repeating ends. So if you want to quench, if you want to stop the chain reaction, what happens is you can actually add another free radical that will actually combine and form this kind of a end group which cannot react anymore. Okay, so you can see that this is another terminating agent. This termination can be from this also. So too much initiator is also a problem, because when you put too much of an initiator, they can actually terminate too soon, and you will probably have a very short chains. So it's very important to control the initiator concentration, or you can always add the initiator at the end, so that you can stop all the reactions, terminate the reactions. So by far this is probably the by far a very common way of doing reaction. Many of the polymers are like polyethylene, polypropylene, all of them are actually made through this kind of reaction, to which you need a initiator. Then you have the next step of dissociation of the monomer, then chain growth or propagation, finally termination. So in a way you can think of this is like first step, this is the last step, this is something that goes in between. Okay, when you wait long enough, you basically grow more and more chain. Now here is an example of a free radical, but you can also create an initiator that could be anionic and cationic, especially if you are thinking about working with the different kind of polymer. You also have anionic and cationic initiator based. Okay, so and the chain reaction, as I said, is a very common addition polymerization. What I showed in the previous slide is only polyethylene, but you can do the same thing with other monomers. Like for example, if you have a propylene, instead of polyethylene, if you have a propylene, you would actually make polypropylene. Okay, so only difference between this and this is that this hydrogen is now replaced with a methylene group. Okay, so that is polypropylene, or you can actually have a polystyrene. Okay, so you can see that this H group is now replaced with a styrene group. Okay, and then whereas various other, the polyvinyl alcohols, polymethyl methacrylate, PVC, PVA, polyacrylonitrile, PVF. So these are all, you know, set of polymers typically formed through this kind of a chain reaction, which includes this, you know, free radical or anionic or cationic. Okay, now even though they all look similar and maybe one of the only the, you know, the side group is changing, but you will see a lot of difference in their properties. Okay, if you take a very simple example, polyethylene versus polypropylene, what is the difference? The difference is only here. Okay, so here you have a hydrogen, here that is replaced by a methylene group, that's it. But this small change in one side chain can enormously change the properties. Okay, so because of this bulkier methylene group, the packing becomes little less denser. Okay, so that's why the polypropylene usually has a lower density than polypropylene, and what that means is it would actually have better chemical resistance and higher melting temperature because of this, you know, the packing, and we also know that from energy density point of view, the larger will have higher van der Waals forces, so they kind of interact very strongly, so they can be more thermal resistance, chemical resistance. So we cannot really guess by looking at these two structures. We say, okay, you know, only one small group is changed, so they will look alike or they will behave alike. You cannot say that. Okay, a small change in one functional group changes everything. Another best example is, think about this PVC. Between PVC and polyethylene, again this hydrogen is replaced with a chlorine, completely different properties. Why? Because chlorine is more electronegative. It changes the way the interchain interaction happens through hydrogen bonding, through dipole interactions. The property can be very different. So one small change in one atom can actually change the properties completely, right? All right, so right now we are talking about addition reaction, polymers made through addition reactions through chain reactions. We can also make what is called copolymers. Okay, so copolymer means that having more than one monomer in the polymer chain. Okay, so now the question is, how these two monomers are going to be placed, how are they going to be configured in the main chain? Based on that, we have certain categories. Okay, for example, we can think about a random copolymer. So random copolymer means you take two monomers A and B, you add them up. Okay, you are doing an addition reaction, which is basically a chain reaction. Here, when you do that, this A and B can be randomly placed. So here you have A and then A, after that B comes 3 times, then A, then BB. So this is completely random, there is no order in there. Okay, these are called random copolymer. This random copolymer is synthesized through this chain reaction, which is an addition reaction. Sometimes you can control the reaction such a way that you have an alternating copolymer, meaning you have this kind of a very regular structure, AB, 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 like that. So A can only form B attached to B. Once you have a B, then only A can come, then again B comes. If you can change the chemistry such a way that only this kind of a propagation can happen, then you are creating this kind of an alternating copolymer. Then there is something called block copolymer. So block copolymer means that you create a block of A monomer chain and then make another block of B, and they are chemically linked together. So here you can see that there is a small block of A, then small block of B, then smaller block of A, and repeats. Okay, so block itself repeats. So these are called block copolymers. Now you can actually go beyond 2. You can actually add even 3 polymers also, 3 type of monomers. Then you have something called tri-block copolymer. You can see that first A block, B block, C block, and again repeats A block, B block, C block. Okay, and then there are more complicated topologies also possible. There is something called graft polymer. In the graft polymer, the main chain can have the single monomer type, but you can actually graft them, you can actually make branches through another monomer. Okay, and these are called graft. The B chain is actually grafted to A chain. something like that. Okay, so this can grow in this direction, right? So here are some examples of the previous case. So here you can see that this is a chain reaction, addition reaction by which a copolymer is made. So here we are talking about acrylonitrile styrene. Okay, so the first one is acrylonitrile monomer, and this is a styrene component. Then you have butadiene and styrene. So you can see this is one repeating unit, this is another repeating unit. This X and Y here means that how many blocks of that monomer and how many blocks of the other monomer is linked. Okay, and ABS and TFE, there are many such examples. Now, the I was telling about two reactions. One is chain reaction. In chain reaction, you have an initiator. Initiator creates free radicals. Free radical goes and attack all the monomers, and they themselves become a free radical, and you have a chain reactions. Okay, so chain reaction basically means each one creating its own free radical. So you have an explosive number of free radicals attacking the monomers. There is another type of reaction which is called step reaction. Okay, which is a different kind of reaction. And step reaction typically happens in the condensation polymerization or ring opening polymerization. So what I mean by condensation is that let's take this example. This is actually a polyethylene, PET, polyethylene terephthalate. In this case, you start with a terephthalic acid and then you have a ethylene glycol. If you see here, this molecule has same groups on both ends, and this molecule also has same groups on both ends. Then what would happen is, you would have a condensation of water molecule between these two. Okay, so when two monomers combine together, you release one small molecule which is water in this case. So this is an example of a condensation reaction. So you can see that the number of atoms in the repeating unit is less than the number of atoms in the monomer because something is released. Okay, things are forming to condense something. Okay, and this reaction happens through what is called the step reaction. This is one example, but you have a variety of possibilities. For example, if you have a diacid and dialcohol, you create what is called polyester. This is one example. PET is a polyester. Or you could actually have a diamine and diacid, you would create something like nylon or a polyamide. Or you could have diisocyanate and dialcohol, you create what is called polyurethane. Or you could have diepoxide, both ends having a epoxide, and the diamine, you would create what is called epoxy resin. So on the right hand side, the polyesters, the polyamides and the polyurethane and epoxy, these are all created through a condensation reaction. Okay, but many of the previous cases, the polyolefins are done through chain reactions or addition reactions. Okay, so here I am showing little example of the diamine plus diacid example, how this reaction happens and propagates. So on the left hand side, you have a diamine. What I mean by diamine is there are two amine groups on the end of the group. Okay, so this R1 can be any alkyl group. Okay, this can be a butene group, or it can be a pentene group, and etc. But you have amine on both sides. Then you have another acid, diacid, which means there are acid groups on both. There is a middle block. Okay, adipic acid, succinic acid, and so many other acids are there in which there are acid groups on both ends. So here what happens is, you see, first thing will be this NH2 and this COH group will combine and release one water molecule, right? So you see that this OH and this H goes as water, then the remaining molecule will form a bond here. Okay, sorry. So you see there is a NHCO bond, NNC bonds forms, and it can actually further grow because you see on the left hand side you have amine group, on the right hand side you have an acid group. Another monomer comes in which is a diamine. This diamine can combine with this acid, then you create this kind of oligomer. Okay. Now in both cases, in this case you have both side amine group, it cannot combine with another acid, sorry, it cannot combine with another amine, but you can combine this with another diacid. So here what happens, that this particular OH and this particular H can combine, you basically make a trimer now. Okay, and then now you have COH group here and NH2 group here. So you can bring another diamine and react with this end group. This keeps continuing, okay. Then you see that the repeating unit seems to be this. This keeps repeating over and over when you grow this chain longer and longer. We call this a step reaction because in every step one water molecule is released, okay. It's like a click, one water molecule goes, another click, another water molecule goes, okay. And that's the reason why we call them as a step reaction. And a polymer made through this, we would write something like this entire repeating unit with a subscript of N, okay. So as you can see, this kind of reaction can only happen when the backbone contains atoms other than carbon. In this case, we have this amine groups and oxygen groups and so on, right. So here, through this kind of condensation reactions, various kinds of polymers are made. For example, polyacetyl, cellulose, chlorinated polyether, phenoxyresins, and polycarbonate, and polyphenylene oxide. These are all different kind of compounds that are made through this kind of step reaction. You can also have polymers in which the backbone may contain nitrogen quite a bit, okay. So you can see this nylon 6, nylon 6,6, all combination of nylon typically will have the NC group, NC bond on the top, okay. So you can see that NNC group here, NNC group here, all formed through this condensation reaction, right. And not only, so the previous cases are all example of thermoplastics, but you can also create thermoset through this condensation reaction. So the examples are this melamine formaldehyde resin, or urea formaldehyde resin, or even polyphenol, which is phenol formaldehyde resin, okay. So so you can see that this broadly speaking, thermosets, plastic could be made through either stepwise or condensation reactions, okay. I think I'm pretty much done with that, so I'll stop here.